Good afternoon, and thank you for joining us here in Garching, Germany, at the headquarters of the European Southern Observatory, or ESO for short. Thank you to everyone watching us online as well. Today, we'll be hearing from the Event Horizon Telescope collaboration about their newest results, so please do switch off your mobile phones to hear them. I'm Barbara Freire, I'm the media manager at ESO, and since we don't have much time until the main results go live in multiple press conferences around the world, I'll quickly present the format of today's event. First, we will hear from ESO's Director General, Xavier Barcons, and then from lead Event Horizon collaboration scientists about the main research. We'll then open the floor for questions from journalists only, be it those here in the room or those watching remotely. I will now hand over to Xavier to open the proceedings.
Hello, thank you. Good afternoon. Warm welcome to ESO to everyone. It's a really great pleasure to be here today, hosting the members of the Event Horizon Telescope collaboration as they prepare to announce their most anticipated results following the unveiling of the first image of a black hole back in 2019. Today, we're going to see something really new, exciting, extraordinary at the center of our galaxy for the first time. We've been so close to it many times before. ESO facilities like the Very Large Telescope and the VLT interferometer, in addition to the Keck telescopes in the US, have observed stars moving around the compact invisible object at the heart of the Milky Way. And for sure, the ESO Extremely Large Telescope will continue doing this in the future towards the end of the decade. The movements of these stars have been tracked for decades using specially crafted instrumentations. These measurements offer the best and very solid evidence so far that these stars can only be orbiting a supermassive black hole. Reinhard Genzel, who is with us today, thank you very much for joining us, was awarded the Nobel Prize back in 2020 together with Andrea Ghez in the US for exactly this discovery. But we are yet to see direct visual evidence of this compact object, which astronomers call Sagittarius A star. This extraordinary result would not have been possible to achieve by one single facility or even by the national astronomical community of a single country. It took 8 radio observatories around the world, and that network has already expanded to 11 today. Many built, funded, operated, and supported through international organizations across many countries around the world. Among those, ALMA and APEX in the Atacama Desert of Chile, which are co-owned and co-operated by ESO, as well as European facilities like the IRAM 30-meter telescope in Pico Veleta and the NOEMA array in the French Alps. It also involved an international team of about 300 scientists, plus many others supporting them, like engineers and many more people. And altogether, it shows what we can achieve when we cooperate, when we work together. This is very important to remember in the times that we are living in, where the world is not running in that direction, unfortunately. ESO was founded 60 years ago, precisely to foster international cooperation in astronomy, so we can jointly tackle the biggest open questions in the universe. And indeed, a key motivation for ESO to put its telescopes in the Southern Hemisphere was to enable science to be done around the center of the Milky Way. So this is why it's such a big pleasure today to be here hosting this event. Together with me, I have 2 of the leading figures of the collaboration, the EHT project director, Joop van Lankevelde, chief scientist at JIVE and also professor at Leiden University, and the founding chair of the EHT board, Anton Zensus, director of the Max Planck Institute for Radio Astronomy in Bonn. Anton will later be telling us about the European facilities involved in the EHT, and now Joop will now present the main result. So over to you, Joop. Thank you very much.
Thank you, Xavier. When I entered the field of radio astronomy as a student, I was told about this enigma, this mysterious radio source Sagittarius star at the heart of our galaxy. I observed it at long wavelengths, and there it appears to be blurred. It's very exciting here today to show you today this best ever image of that enigma Sagittarius star. I will do that with my team, or with the team, but I would first like to remind you that the team is much bigger than fits in this audience. In fact, it's bigger than fits in the auditoria around the world where this press event is taking place simultaneously. We are over 300 people on these papers, and only very few of us get to be staged here today to share the result with you. To share the result, we will be flying into the heart of the galaxy, some 27,000 light years away from us. We will do that in 45 seconds. That's a violation of Einstein right away, but maybe that's probably the only violation of Einstein. So we start out from the plains of Chile, where the ALMA telescope is located, and we're going to zoom in to Sagittarius, the Archer, which is high in the sky above the northern Chile. And we will go and zoom in first in the optical, but we have to switch to the infrared because there we can penetrate all the way into the galaxy. We leave tens of millions of stars behind, and we get to the place where stars are in orbit around a dark spot. And when we switch then to our radio eyes and we use a network of telescopes to resolve further and further, I can present to you the image of Sagittarius star, the black hole at the galactic center. I will now introduce my team in reverse order here on stage, because that went really fast. Christian Fromm is from Frankfurt and Würzburg University. Maria Felicia de Laurentiis is from the University of Napoli and the Italian Nuclear Research Facility. José Luis Gomez is from the Instituto de Astrofísica de Andalucía in Granada. Thomas Kriegbaum is from the MPI in Bonn, but to lead on explaining what we have seen and what it all means, Sarah Issaoun is from Harvard and Smithsonian and Radboud University.
Thank you, Hub. Ooh. This is the first image of the supermassive black hole at the heart of our Milky Way galaxy, Sagittarius A star. For decades, we have known about a compact object that is at the heart of our galaxy that is 4 million times more massive than our sun. Today, right this moment, we have direct evidence that this object is a black hole. The black hole resides inside the dark region at the center of this image, where its gravitational pull is so strong that light cannot escape, and only darkness remains. We call this region the shadow of the black hole. This region is surrounded by very hot gas swirling around the black hole. This gas emits radio waves we observe with the Event Horizon Telescope. These radio waves create the glow we observe around the shadow of the black hole. From our image, we measure the size of the shadow of Sagittarius A star to be 52 micro-arcseconds on the sky. This is about the size of a donut on the surface of the moon as seen from Earth. In reality, Sagittarius A star is about as big as the orbit of Mercury around the sun, but at a distance of 27,000 light years. Because the size of a black hole shadow is proportional to its mass, our image tells us that the mass of Sagittarius A star is 4 million times greater than that of our sun. It is really incredible that this prediction from Einstein's theory of general relativity matches the mass measured by the Nobel Prize-winning studies of stellar orbits in our galactic center. Today's image might look familiar to some of you. We were all amazed that the image of Sagittarius A star looked so similar to that of the famous black hole in the M87 galaxy, an image our team revealed back in 2019. However, Sagittarius A star is over 1,000 times less massive than M87 star. If Sagittarius A star were the size of this donut right here, tiny, M87 star would be the size of the Allianz Arena, the Munich football stadium just a few kilometers from where we are today. On top of that, Sagittarius A star consumes gas at a much slower rate than M87 star. And these two black holes also reside in completely different environments. Sagittarius A star resides at the center of our small spiral galaxy, whereas M87 star resides at the center of a giant elliptical galaxy and ejects a powerful jet of plasma. Despite all these differences, the images of these two black holes look very similar. Why is that? This similarity reveals to us a key aspect of black holes. No matter their size or the environment they live in, once you arrive at the edge of a black hole, gravity takes over. The journey to the edge of Sagittarius A star spanned decades of technical and scientific developments, and I will pass it on to my colleague Thomas to tell you all about our adventure. Thank you very much.
Thank you, Sarah. Imaging a distant black hole would not have been possible without a big telescope of very high magnifying power, or angular resolution, as we astronomers call it. To achieve this, astronomers combine radio telescopes located around the globe to create a super telescope which has the size of the Earth. This technique is called Very Long Baseline Interferometry, or short VLBI. While the Earth is rotating, all telescopes observe the same astronomical objects for several hours. At each telescope, the data are recorded on hard disks and are accurately time-tagged by precise atomic clocks. After observations, the data are shipped to processing centers where they are combined in supercomputers. These supercomputers are called correlators. After a number of quite complex data analysis steps, this results in the high-resolution image of the radio source. It took more than 25 years to optimize this observing technique and make it work also in the short wavelengths 1 millimeter band, where the angular resolution is highest. It required the development of quite complex and very technically challenging techniques and data acquisitions so that the wider observing bandwidth could be used to achieve this better sensitivity. This sensitivity is really needed for the accurate imaging of the faint event horizon scale structures which we are now seeing in Sagittarius A star. A decade of pilot studies paved the way in Europe and in the US for the formation of the Event Horizon Telescope. The EHT is a VLBI network of telescopes which combines radio waves at 1.3 millimeter wavelengths. This wavelength is short enough to see the swirling matter around the black hole. During the Sagittarius observations in 2017, the EHT combined 8 telescopes. Since then, the network has already grown to 11 nowadays. The radio telescopes of the EHT are located at particularly high sites to minimize the influence of the atmosphere and the water vapor on the observations. Examples are the ALMA and APEX telescope in the dry Atacama Desert in Chile, the IRAM 30-meter telescope in the Sierra Nevada close to Granada in Spain, and the NOEMA interferometer in the French Alps. With this, the EHT achieves an angular resolution which is sufficient for the imaging of such distant black holes, and also sufficient for the matter surrounding these black holes. To give you an idea, the EHT can see 3 million times sharper than the human eye. So when you are sitting in a Munich beer garden, for example, one could see the bubbles in a glass of beer in New York. Sagittarius A star was observed by the EHT in 5 observing runs during April 5 to 11 in 2017. These telescopes also included, for example, special places like the South Pole. The telescopes recorded a total of 6,000 terabytes of data, which were then shipped to the 2 correlator centers, one being in Max Planck Institute for Radio Astronomy in Bonn, and the other one at MIT Haystack in Massachusetts, close to Boston, in the US. The amount of processed data is really very, very huge. It would basically, if you would print this data on A4 paper, the paper stack would reach the moon. Of course, we are not going to waste such much paper. After correlation, the calibration and sophisticated data analysis took several years and required the development of many, many new tools by the members of the EHT collaboration. In this development, we also honor the substantial contribution of very many young scientists who just start their careers now. For the details of this amazing imaging process, I would like to refer to my colleague and the next speaker, José Luis.
Thank you, Thomas. Thank you very much. Yes, as my colleague Thomas mentioned, the EHT is like a giant Earth-sized telescope, but it doesn't work like a regular telescope. Instead, the radio telescopes of the EHT work in pairs, with each pair collecting the information required to obtain an image. As the Earth rotates, the separation and orientation between telescopes changes, providing this extra data that we need. With the 8 radio telescopes of the EHT, we have enough information to obtain an image, making the EHT the only existing instrument humanity has to image supermassive black holes. Imaging Sgr A was, however, significantly more challenging than M87. Oh my God, it was really a lot harder. Our line of sight to the galactic center is obscured by matter, which scatters radio waves coming from the region around the black hole. But most importantly, as shown in these computer animations, the gas in these 2 black holes moves at the same speed, nearly as fast as the speed of light. But Sgr A star is over 1,000 times smaller than M87. This means that the time that the gas takes to orbit Sgr A is only just a few minutes, while it takes days to weeks to orbit the larger M87. This means that the gas around Sgr A was actually changing while we were observing it. It was like trying to take a clear picture of a running child at night. So you would imagine how difficult and how crazy it drove us for many years. So we EHT scientists have developed sophisticated new tools to account for this rapid movement of gas around Sgr A star. Tens of millions of images of synthetic data created to best resemble that of Sgr A star have been produced in supercomputers around the world to refine all algorithms, like searching for the best lens and filter to get the sharpest ever image in your camera. The EHT collaboration has produced thousands of images of Sgr A star using classical methods and EHT tailored new algorithms for imaging interferometric data. As shown in these images, each one of these images is slightly different, but by averaging these images together, we are able to emphasize the common features finally revealing the giant Larkin at the center of our galaxy for the first time. But it is important to note that not all images look alike. We found that we can cluster these images into 4 different categories. The vast majority of them are contained in 3 clusters with only ring images that only has some changes in the brightness distribution around the ring, and only just a minor cluster with images that doesn't look quite like ring images. Through literally years of exhaustive tests, we are now confident to have captured the first image of the black hole in our galactic center. Sagittarius A star now holds the record previously set by M87 of the most thoroughly vetted interferometric image that has ever been made. Our detailed analysis of the images, as well as exhaustive modeling of the interferometric data, has revealed that all share exactly the same ring size, precisely measured to be 52 microarcseconds, in perfect agreement with the size predicted by prior observations and theory. Of course, we are thrilled today to show the first image of the black hole in our galactic center. This, together with the previously release of an M87 image, fulfills the initial visionary goal of the EHT. But this actually only marks the beginning of an amazing area in the study of black holes. The ongoing expansion of the EHT and the significant technological upgrades will allow scientists of the EHT to release even more amazing images and, of course, movies of black holes in the future. And now, to learn what this image tells us about the black hole itself, I pass it on to my colleague, Christian. Thank you.
Thank you, Jose. To interpret the image and to learn more about black holes, we performed detailed models how the gas and the light behaves in the direct vicinity of black holes. Our models have 4 ingredients: the black hole, magnetic fields, gas circulating the black hole, and the light emitted by the gas, which is finally collected by the telescopes of the EHT. Astrophysical black holes can be fully described by their mass and their rotation. Black holes can spin either in the same direction as the gas or in the opposite direction. For the model or for the image and the source in the galactic center, we know the mass estimate very good from stars orbiting it. However, the spin of the black hole in the galactic center is rather unknown. In our models, we let mass and matter fall towards the black hole, and this matter forms a disk around it. The gas in the disk is circulating the black hole and heats up. While the gas is heating up, it starts glowing. So thus, in the EHT image, we see the glow of the infalling and outfalling material. Similar to the black hole spin, we don't know exactly what is the orientation of the black hole towards the Earth. And changes in the orientation lead to different image structure and different positions of the bright spot around the ring. Therefore, our modeling needs to cover a large range of possible spins and inclinations. Therefore, we built the largest and most detailed image library for black holes ever. For this purpose, we use supercomputers around the globe, spending billions of CPU hours creating petabytes of data. Finally, we have obtained millions of black hole images, and we compared them not only to the EHT data, but also to historical and complementary data. Our best bet model, which is playing now, shows a lot of fine details. You can see these fine arcs going around the black hole. However, when we consider the resolution of the Event Horizon Telescope, as my colleagues explained, these fine features are blurred out. And you will see this soon. This will switch on to the blurred image. So now you see the transition to the blurring. Now the fine features are gone. This is the resolution of the Event Horizon Telescope. What we found is that the black hole in the galactic center is rotating, and it's seen face on. The implications of our modeling with respect to theory of gravities will be explained by my colleague, Maria Felicia. Thank you.
Thank you, Christian. As our nearest supermassive black hole, Sagittarius star can be studied in ways that are not possible for other sources, making it a unique laboratory for exploring the astrophysics of black hole and testing prediction of Einstein general relativity. We relaxed the assumption that Sagittarius star supermassive black hole is described by Einstein theory and quantify possible deviation. Our finding from this new measurement of Sagittarius star provide further evidence that astrophysical supermassive black hole, independent of their mass, are described by solution of Einstein theory. For Sagittarius star, as we found for M87, the inferred size of the black hole shadow is consistent with the prediction of general relativity within the 10%. This consistency is inspired of the fact that Sagittarius star and M87 are feeding on matter at dramatically different rates, with Sagittarius star accreting 1 million times less matter. So our conclusion indicate that Einstein theory is still holding strong. And in addition of what was observed for M87, now we have the most compelling evidence to date that the supermassive compact object at the center of our galaxy is a black hole, and that it is in all likelihood described by Einstein theory. We know black hole, and in particular the vicinity of the event horizon, are becoming an observational test bed for gravitational physics. This environment offers us the unique opportunity to determine where and how Einstein theory breaks down. And if it does, of course, will transform our understanding of gravity and the property of space and time. We know very well that the idea of testing Einstein theory using our galactic center black hole is not new. But the result we have shared today represent an important step forward. So I'm delighted to be able to say that we have finally imaged the supermassive black hole at the heart of our galaxy. These measurements have opened a new window onto studying black hole and their role, their central role in our universe. The years ahead, of course, will transform our understanding of black hole and the fundamental nature of gravity. So stay tuned, because the best is yet to come. Now, I will hand over to my colleague Anton, who will give the closing remark. Thank you.
Good afternoon. This is it. This is it is a huge moment for everyone in the Event Horizon Telescope collaboration. It's the next level. And I'm proud of everyone, of our entire worldwide team. They have worked so hard for this latest breakthrough. You are the first to see our image of the black hole in the center of our galaxy, as close as it gets. Imagine this. We have combined the world's greatest radio telescopes into one Earth-sized camera. To be honest, after doing this for 40 years, I'm still astonished each time we pull this off. Let's shine a spotlight on the European facilities within the EHT, and we begin with the ALMA Observatory. The Atacama Large Millimeter Array at 5,000 meters altitude in the Chilean desert. This was our game changer. Its sensitivity, because of its huge collecting area, was the difference in measuring the weakest signals. And the 30-meter antenna in Spain of IRAM, this has been our flagship for over 2 decades. It is essential for making the sharpest image. The APEX, the Atacama Pathfinder experiment in Chile, near Alma, is invaluable for precisely calibrating our signals. And the NOEMA, the Northern Extended Millimeter Array in the French Alps, with this huge collecting area and super sensitive receivers, has given a further boost to the EHT. And a supercomputer, our correlator, is a hub for the processing of the enormous data sets that are required to then extract our images. These facilities, which include the 3 largest antennas within the EHT, and the support from our funders, and yes, that's us, the taxpayers, are a sustainable foundation for the continued success of the EHT. And we acknowledge the support of the national funding agencies, of the European Research Council, and of the Commission. Now that said, in its DNA and by our design, the EHT is a truly global enterprise. Well over 300 scientists from over 20 countries, and add to that telescope designers, builders, engineers, technicians, and staff. Their contributions are what the scientific collaboration depends on. In 2019, a little over a century after Albert Einstein revealed his theory of relativity, and after decades of pioneering preparatory work, we presented the first image of a supermassive black hole in the center of the galaxy M87. Nobel Prize-winning measurements by Andrea Ghez and Reinhard Genzel, and we're so happy, Reinhard, that you're with us. With their teams, they showed that there must be such a black hole in our galaxy, and we made this black hole visible for the first time, and it confirms their conclusions. So what about Einstein? Would he smile seeing all this, hundreds of scientists still not having proven him wrong? I rather think that he would be ecstatic, seeing all the experimental possibilities we have in this field today. So, mission accomplished? Yes, but there's so much more to do. We now want to go on, make movies. We want to study magnetic fields. We want to look at the jets in galaxies. And yes, we want to tackle gravitation theory again. New antennas in the EHT, like NOEMA and the African Millimeter Telescope, and ever-improving technology will enable us to do that, and much more. So today we're celebrating the first image of the supermassive black hole in our galaxy. And we're talking about what it tells us and why that matters. And tomorrow we'll be back at work unraveling the mysteries of black holes in the universe. Thank you all for being with us today, and now over to your questions.
Thank you to our speakers for sharing this remarkable result with us. Before I open the floor for questions from journalists, I'd like to remind everyone that we have extensive press material, including images and videos, on ESO.org. For those of you watching online, please stay tuned, because at 4:30 we have a Q&A panel where members of the public will be able to ask questions to EHT experts. But on to questions from the media. If you are a journalist here in the room, please raise your hand. Take your mask when asking a question and speak very closely to the microphone, otherwise we cannot hear you properly on the stream. Do identify yourself, whom you are reporting for, and whom the question is for. And then we will answer questions from members of the media watching remotely, who have sent in plenty of questions already, a little later. So do we have any questions in the room from journalists or media participants? All right, if not, we can start. Oh, okay.
Hi, so I'm Teresa Paneke. I'm actually a PhD student here at ESO, and I do science communication online through social media. So thank you very much for this amazing result. I would like to ask, because We've talked a lot, or it's been said a lot, that M87 has an active black hole, whereas our black hole is maybe not accreting as much material. So when we just look at the image, they seem to be equally bright. Of course, there's the distance difference, but what exactly is the material we're seeing there? Do we have an idea about accretion rates? So what is the difference between M87 and Sag A in that regard?
So as you already heard, the difference is the central mass already. So the galactic center has roughly a mass of 4 million solar masses, as Professor Gensel showed us already, and M87 has billions of solar masses. The other difference that you may have noticed on my animations or from images of M87 is a powerful jet that is generated in M87. For the galactic center, we see it, as I showed you, phase on. So the jet, if it's existing, is pointing towards us. It's very dilute, so we can't, at the moment, image it, and I would refer then to my colleagues to explain you a bit what we need to finally detect it. And I think these are the three major differences. It's the mass, it's the jet that's existing, and as already you said, it's a different mass accretion rate, which we have for both systems. So maybe one of my colleagues.
Yes, thank you very much, Christian. Yes. In order to obtain the image, we need to have measurements of with antennas at different separations to measure features that are very small and features that are very large. So in order to capture a possible jet in Sag A star and to actually capture the jet that we do know exists in M87, we need to have measurements of telescopes with short separation to see these larger scales. We lacked that information during 2017 observations, and this is why we did not see the jet in the M87, and we have not seen any jet in Sag A star. We do have new antennas in the observations that followed the 2017 campaign, and we do expect to see the jet in M87. It is still unclear how bright, if there is a jet in Sag A star, but we will be chasing it, of course.
Thank you. Yes?
Hi, thank you so much. This was very exciting for me. My name is Camila. I am with the Brazilian podcast Astronomia em Meia Hora. And I wanted to ask if the collaboration has other targets in mind already, anything like planned to observe in the future.
Well, thanks for the question. Yes, of course, we have other targets in mind. I mean, during these observing runs, we not only observed M87 Sagittarius A star, but we observed also a number of AGN, some of which are very close by. And data analysis of this is still ongoing, but give you a warning, since they are so distant, we will be not able to see these beautiful shadow-like images immediately. So it would require more sensitivity to really look at the very closest objects, and we are at the moment surveying the sky to find these.
Thank you. I'll take questions online now because the list is piling up. So this one is from Hans Heckenberg from New Scientist Dutch edition, and it's addressed to Sarah. What open questions that we currently have about the structure of black holes can be answered by this image and follow-up images of Sag A star?
Ooh, that's a loaded question. Yes, so open questions that we can answer. I think Kristen's portion of the presentation summarized really well the major things we found out about Sag A star, which is one of the unknowns is the black hole spinning, which we have the answer to that. Yes, it is. And what is the orientation of the black hole with respect to us, which we also did not know before. And now we're fairly confident that it is pointed more or less towards us, so face on. These properties, this knowledge of the fundamental properties of the black hole will help us study the astrophysics of the black hole in more detail later on, and also how we interpret the images. The spin and inclination have very important roles in how the image looks and how we interpret the astrophysics we can learn from it. Future observations of Sag A star, of course, are Current observations from 2017 also have polarization information, which we are planning to start working on, like Anton said, tomorrow. That will tell us information about magnetic fields around the black hole. And magnetic fields can tell us about how the black hole eats gas and ejects possibly a jet or outflow. So as Christian said, we still don't know if Sagittarius has a jet. Some of the models seem to hint towards that direction, but magnetic fields, learning their configuration, how they look around the ring of Sagittarius, will help us answer these questions very soon.
Thank you. Okay, I'll continue with the online questions. So we have from David Castelvecchi reporting for Nature. This is addressed to any of you. How does the measured angular size compare with the mass of 4.15 million solar masses measured by Genzel's group? Would like to take that one? Maria Felice?
Was very important to have their measurement, their astrometric measurement to us, because what we found that the size of our ring of the shadow is consistent with that mass. As Sarah said before, that the size is proportional to the mass and to the distance. For us was important this, and
okay, thank you. All right, we'll continue with the online questions. So from Sanja Venkart, reporting for Wolfgang magazine in Vienna, also addressed to any of you. What are the difficulties when observing and analyzing Sagittarius A star? This might be more for José.
Very happy to answer this. Well, many. I mean, oh my God, where do I start? I mean, the most difficult part of Sag is that it's a very small black hole as compared with M87, 1,000 times smaller than this. And then we had to try to find a way in which we can overcome these extreme changes in the emission that we were observing, as we were explaining before. In order to capture an image of the black hole, we need to take a very long exposure snapshot. We are observing these sources for 8 to 10 hours. And the basic principle of the technique that we are using is that during those 10 to 8 hours, your object is not changing. And this is exactly what refuses to do Sagittarius A. So in order to that, we have created these new tools that allow us to get a little bit blurry image, adding a little bit of extra noise to compensate this variability, so that even though the image may be a little bit blurrier than the image that we got from M87, we do capture the main features, the most salient nature of the black hole. And this is the ring structure and all these images that we were showing before. They all share the same ring size. What we were not able to capture is what is, the brightest emission around the ring. And this is because it's changing. So we are getting these different images, all consistent with a ring, 52 microseconds, but the emission around the ring changes when we make slight changes in the way we make the images. Like we change a little bit the lens, or we change a little bit the filter, and then the image looks a little bit different. But the main image is there. And all this analysis is what took us more than 2 years, from 300 people in the collaboration, from doing the imaging, from doing the analysis, and etc.
Thank you. Okay, I don't see any hands up here, so I'll continue with the online questions. We have one from Filip Ogorzelski from TVP Nauka. This is addressed to any of you again. How much matter is being absorbed by the black hole in the center of the Milky Way? Christian?
I'm not exactly sure what he means by absorbed, but the accretion rate. Yeah. So actually, these black holes in the galactic center is secreting very, very less matter. They are basically, this black hole is basically starving. The accretion rate is extremely low, and yeah, the accretion rate is extremely low. Maybe Sarah.
Apology for that. We had to We calculated this for a fun EHT Twitter poll that we had. So if you were to have the same diet as Sagittarius A star scaled to your mass, you would eat 1 grain of rice every 1,000,000 years.
I would not want that diet.
No.
All right. We have a question from Antonio Pires, reporting for astronomia.com. How much did the telescopes that recently joined the HT collaboration improve the results from the previous observations in terms of resolution and sensitivity? Will we be able to increase the apparent aperture by using space telescopes in the foreseeable future? This be perhaps for Thomas?
Well, first, of course, this image which we created now has the same configuration. So the 2017 data of M87 and Sagittarius A star based on the same telescope configuration. In 2018 and following observations, we have added more telescopes. Now we have 11 telescopes, so we fill the UV plane much better. That means we can much better make a synthetic telescope, and the participation of NOEMA and also of KidPeak, for example, provided additional baseline sensitivity. We also expanded the recording rates and doubled the observing bandwidths. So all this lets us hope that in 2022, where we just observed the source again a couple of weeks ago, we will get a much better image.
Thank you. Okay, we have one from Dave Adalian, reporting for earthsky.org, and I think Christian would probably be able to answer that one. When the orientation of Sagittarius A star is said to be face-on, does that mean one of the black hole poles is directed towards Earth? Do we know how fast Sagittarius A star processes, and what is the nature of the particles ejected?
Okay, so let me start first. So we found that it's face-on, so this is correct, that one of the spin axes is pointing more or less towards us. The other part was about the material, or the emission actually that we see, and what we model is synchrotron radiation. So you have particles, mainly electrons, gyrating magnetic fields, and while they gyrate the magnetic fields, they emit emission, and this emission is synchrotron. And this is what we actually see. And there was a third part. Could you please repeat this?
So it was the processes.
Yes. So precession, I think what you mean is spin. So what we have actually is we have some kind of best bet models. So we have not found an exact model which could explain everything. So we have best bet models and best bet regions. And there we could say that it's spinning, and it's spinning in the same direction as the gas orbiting it, but the precise number of the spin has to be obtained in upcoming observations.
Thank you. Okay, we continue with the online questions. We have one from Roberto Peixoto, reporting for Geo Globo in Brazil. EHT observatories capture radio waves, but how do black holes emit these waves, and how can we build an image with it? Who wants to take this one?
Emission, how it produced is I already explained. That's the synchrotron radiation. So basically you accrete gas, which is electrons, they gyrate, produce the emission. And for the details of how we actually detect this and so on, I would refer to one of my colleagues working on data processing and imaging.
Is that for José, Thomas?
Yes. Then the most important part, of course, is to get an image. As we were explaining before, the EHT doesn't work like a regular telescope, so we cannot build a telescope the size of the Earth, obviously. We cannot do this. But what we do is we have these different telescopes that act like segments of this huge telescope. And then we collect the signal from all of them and create, synthesize the virtual telescope on a computer. Once we do this, and then it is possible to have basically like the Earth-size telescope and get an image like you would get an image with your mobile phone. But it is significantly more complex. You have to do you have to make the images on supercomputers. So it's a process which is extremely complicated, but at the end, you are able to finally obtain the images of these supermassive black holes.
Okay, thank you. Another question online is from Doris Urrutia, reporting for Inverse. How did you feel when you saw this new result? What was the big reason that you felt excited enough with your finding to share it with the world? Who wants to take this one? Sarah?
Yeah, so I did my PhD research on Sagittarius A star, trying to chase down this jet that is maybe real, maybe a myth. And so I was working on images of Sag A star at a lower frequency than EHT, so images that aren't quite at high enough frequency to be able to peer through all the gas and see the shadow. And I was trying to understand where this radio emission comes from near Sag A star, try to see if we could constrain the inclination of the black hole from my observations. And until today, I was also the record holder for the best image of Sag A star. So when working on EHT, I saw the image of the shadow. It was a really special moment because I've been working on this source for a long time through my PhD and trying to understand its properties, and there it was, staring back at me, and I felt, shivers and excitement, and it was revealed as part of the whole imaging teams coming together, just like for M87. We're all on a Zoom call. I was in Japan with a few people at a Galactic Center conference, which was quite funny. It was midnight, Japan time, when we had the telecon, and we all huddled together, and the images, like Jose was leading the telecon, images were revealed from all the different teams, and everybody saw this ring of the same size. And it was such an exciting day and very memorable to finally see this object I've been working on for a long time.
How? Did you want to add?
I wanted to say one thing to Sarah. She's still the record holder.
Yeah, but now I have to share it.
Did you want to add something as well, Thomas?
Of course, this is all correct, but as a little bit older person, I realized how it all started. And I think it took now more than 30 years to get the image. So we had this idea long ago, and at that time when we started observing, the first experiments at 1 millimeter failed horribly. And we have to step back to 2 millimeter before we could do it at 1 millimeter again. And I saw that over the years, the techniques have improved so much. That's really a very, very good feeling to see now that it has worked and that we are now finally able to show that image.
It's great. I'm also very glad that you are able to share it. Okay, one more question online. It comes from Diego Garcia, reporting for Canal Sur TV. This is addressed to Jose because he wants you to answer in Spanish, but someone else could answer in English as well, I suppose. During this process, what have you discovered at a scientific level about Sagittarius A star that was not known before? And then there's a second part to that question. What are the biggest differences between this image and the one of the black hole in M87?
Okay, thank you very much, Diego. I probably should answer this in English for the whole community. Thanks again for your question. Yes, I think the most important thing we have learned is that first we have the visual confirmation of the black hole that was predicted a long time ago. As my colleague Christian mentioned and Maria Felicia, now we have a constraint about how fast this black hole rotates. And this is very important because we think that the rotation of the black holes provides the energy that powers this huge jet that we see like in M87. And the second part of the question was probably...
So there was one about the differences, and
yeah.
My colleagues moved the question already. So
all right, okay, it's fine.
If they can fetch it.
Sure, no, it's fine.
Okay.
Fine. Sorry, I forgot.
It's important also because we, for the second time, we were so close to the event horizon, and then we were able to test gravity at a different regime, at different scale, and we were surprised also that general relativity is still holding, it's incredible.
So I have the question back, and it was two parts. What have you discovered about Sagittarius A star that was known before, and the differences between the images between M87?
Yes. Well, the images are surprisingly similar. I mean, as we were discussing, these two black holes they both live in completely different environments. Yet, at the end, the image is just mainly made out of the gravitational pull, as Sarah was mentioning. So, in that sense, this confirms one of the most important predictions from general relativity, which is that these are the most amazing, extravagant objects in the universe, yet the simplest. They are just you know, as simple as a you know, a sphere or a circle in our images. Thomas?
Well, also with regard to the published results from gravity, I think there's a major difference. M87 is far away and it's much bigger, so it varies much slower. But in Sagittarius A star, we really can see the variations. I mean, we see basically bright features moving around. Although we are not able really to trace their motion exactly, we have published in our papers some models which explain this motion already. And I think the next step would be to parameterize the motion so that one can do more science out of it.
Thank you. Okay, I will continue with the online questions. We have one from Alejandra Lopez reporting for El Tiempo in Colombia. This is to any of you. So she asks, perhaps Christian, what is the orientation of the rotation of this black hole with respect to the plane of the galaxy? Do we have an answer to that?
So what I mentioned is we see it face on, and according to our models and this bad region, the rotation is in the same direction as the gas. And please, all my colleagues, correct me. It's in a counterclockwise way when you look on it. When you look at the images, it's turning counterclockwise. At least in the simulations. So the simulations, you see that it's turning in a counterclockwise way.
Okay. We have time for one more question. I'll give priority to journalists here in the room. If not, I'll continue with the online questions. And we have one from Tushnet Physics World. Do we have any ideas on why there is such mass difference between Sagittarius A star and M87 when they are both supermassive black holes? Who wants to take this one? How?
Okay. Am I on? So that's most likely to do with the evolution of the galaxies in which they are found. M87 is a very giant elliptical galaxy, and it's probably the result of merging many galaxies with many black holes together, while our galaxy has been going through much less evolution.
Okay, thank you. All right, I will stop now because we are almost at the hour, and I will thank our speakers again, and thank you all for the questions, also for those watching remotely. Journalists are now welcome to approach our panelists and other experts in the room. So EHT experts have a badge with an orange color in it. And then there are also other experts who are not part of the EHT team, but can answer questions about the research, who have a badge with a green color. And we have interview areas available here and up there, and you can approach myself or one of my colleagues to be guided to them. For members of the public watching remotely, do stay tuned, because we have a YouTube Q&A coming up at 4:30. And then, before that, we'll actually have a special musical performance just before this Q&A session. Do go to @ESO on Twitter to find out more about it. Thank you all very much, and thank you. Thank you.
So, welcome everyone once again. We're here from the European Southern Observatory in Munich, Germany. Very, very excited about this amazing image we just saw of our own black hole, Sagittarius A star. And of course, as you already heard and know, this has been a worldwide collaboration. The Event Horizon Telescope is a collaboration of several telescopes around the world. And just like there are several telescopes around the world, we also have several black hole fans around the world from all different areas. And this is why today, before we go into a very interesting Q&A conference through YouTube that you will be able to follow from your houses and from wherever you are, we have very, very special guests that want to share the love for black holes, for astronomy, and for music with all of us. It is my greatest pleasure and honor to introduce to everyone Win and Regine from the band Arcade Fire. It is amazing that you guys could join us all the way from the other side of the world. So hello, guys. How are you feeling? How are you feeling about this amazing image?
Oh, it's incredible. I mean, our new record is called We, and I feel like this whole project is very symbolic of what can happen when, you know, humanity works together. It's a really incredible moment.
Exactly. So Arcade Fire just released last week this new album We, and one of the records actually references to our black hole Sagittarius A star. So could you guys tell us a little bit about this? Where did this idea come from? Are you black hole and astronomy fans too?
Well, I mean, I feel like to me it's almost symbolic of there's so much we don't know about ourselves and our planet, and when I was reading about Sagittarius A, it just sort of spoke to me as like this enormous thing at the center of our galaxy that we don't fully understand, that we're like trying to understand better. And and also just the sense of collaboration that it takes to kind of get these images, and just like it's like transcends international borders, and it's sort of in all of humanity's common interest. And so I think that, you know, it's important to look up to the stars and to get out of our own heads. And it's very easy to be like, you know, our album just came out and we're worried about all of our little problems, and it's great just to look up to the sky and kind of work together and think about things that are much bigger than ourselves.
Absolutely. That is exactly what astronomy is about, the international collaboration. That's what we're very interested at doing here at the European Southern Observatory, and of course what EHT, the Event Horizon Telescope, is about. So coming back to the song, did you have the opportunity to see maybe the first image of a black hole, the M87, this big donut orange image that was released 3 years ago? Was this also a source of inspiration maybe for you guys to imagine when you were doing the creative process of the song?
Yeah, I mean, it's actually, an image of it is on the back of our LP, so it's sort of, we sort of superimposed it with an image of an eye, human eye, very close, and there's like a lot of links between the stars and ourselves.
Very similar to what EHT does, right? Like just creating a huge simulated telescope of the size of Earth. So it is my impression that today we will actually get to hear this very exciting song called End of the Empire for Sagittarius A star. Am I correct?
That's right. Yeah.
So whenever you guys are ready to surprise us with your music.
Okay, great. We're gonna sing for you guys. Hold on. Hi, everyone around the world watching. This song is called Sagittarius A. I unsubscribe. I unsubscribe. This ain't no way of life. I don't believe the hype. She unsubscribes. She unsubscribes. She says, there's diamonds in your eyes.
midway through life. Unsubscribe. Virgil says, take a ride. Unsubscribe. You'll need a divine guide, 'cause this inferno's hyperdrive. Child and on the way. Why don't we name him Sagittarius A? What a pretty name. We unsubscribe from season 5. Anyway, the clothes don't fit me right. Sagittarius A star. We'll see one day where you are and what's on the other side. This song is called We, and this is sort of like the imagination of when you actually get there, what's on the other side. So I'll just start this one, Regine. Peace and love. We're all one people. We all have the same mother. And this is the only planet we got. Thank you for all your hard work, everyone around the world. What a beautiful moment for humanity.
Thank you so much, Wen and Regine, for that amazing, amazing performance. What a treat to have you with us. And for all of you that, of course, are buzzing with questions and excitement, we want to remind you and invite you to be part of what comes next in the streaming of this new Sagittarius A star image announced by AHT here from ESO. We will have now a YouTube Q&A for you to ask each AHT experts and panelists your questions. So remember to connect through social media and the YouTube chat so you can ask all your questions, and we'll be right along with the Q&A. See you. Bye.
Keep looking up.
Hello, good morning, good afternoon, good evening, depending on where you are joining us from. My name is Juan Carlos Muñoz. I'm the media officer at the European Southern Observatory here in Germany. And if you're following us, you probably know that this is going to be a Q&A session with some members of the Event Horizon Telescope, the team who just revealed the very first image of the black hole at the center of our galaxy, which you can see here. This is a historic occasion. This is really the black hole lurking at the center of our galaxy, imaged for the very first time. Doing this required quite a lot of quite a large technological and scientific effort because there is no single telescope that can capture an image so small like this. The black hole is 27,000 light years away from us. So even though it's intrinsically really big, it is very, very small on the sky. So the Event Horizon Telescope team had to combine antennas all over the world to make like a huge, gigantic Earth-sized telescope in order to be able to take this image. Now, if this image looks familiar, it's because it's very similar to the one that the same team released a few years ago of another galaxy, the Messier 87 galaxy. But this one is more special because it's ours. It's really in our own galaxy, in our universal neighborhood. Imaging this black hole was not an easy feat, and we will discuss this afternoon what were the main difficulties that the team had to do this. If you want to ask questions, there are several ways to do that. One of them is through Twitter. You can use the hashtag #AskEHTEU. You can also do it from the YouTube stream. So if you don't see the comments section in the upper right part, just refresh your browser and it will appear. So you can either ask the questions there or through Twitter using #AskEHTEU. If you're following us on YouTube here, just feel free to say hi in the chat. Tell us where you're connecting from, because we like to hear from you. So yeah. We really hope that you enjoy this, and let's introduce the panelists. So first we have Professor Sarah Merkov. Hi, Sarah. How are you?
Hi, Juan Carlos. How are you?
I'm fine, thank you. Thank you so much for joining us. So Sarah is a professor at the University of Amsterdam and within the Event Horizon Telescope collaboration. She is the vice chair of the Science Council, and she also coordinates the multi-wavelength campaigns, the working group that takes care of the observations with different wavelengths. From all the papers that the collaboration just put out today, she coordinated the first one, which is like an overview of the whole result. And her scientific expertise is modeling black holes. So any questions you have about black holes, she will be able to answer them. So thanks again, Sarah, for being with us here. Then we have Michael Jansen. How are you?
Hi, I'm good.
So Michael is a postdoctoral researcher at the Max Planck Institute for Radio Astronomy in Bonn, here in Germany. And he coordinated the second paper that the Event Horizon Telescope released today, which focuses on the observations at different wavelengths, the processing of the data, and the calibration of that data. He also participated in some observations, like with a large millimeter telescope in Mexico. And he also processed and prepared data gathered from all the telescopes, which then enabled the team to actually make the final image that you saw today. So welcome, Michael.
Thank you.
Next up, we have Rocco Lico.
Hi, Juan Carlos.
How are you, Rocco?
Good.
So Rocco is a postdoctoral researcher at my home country in Spain, the Instituto de Astrofísica de Andalucía. But he's also affiliated with the Italian National Institute of Astrophysics. His research, like many other members of the EHT team, focuses on the physics of supermassive black holes and their jets. He worked within the imaging group, so this is the team that took all this super complex data that was gathered by telescopes all over the world to combine them into like the final image that you saw today. And he's also part of the management team of the Event Horizon Telescope collaboration. So welcome, Rocco.
Thank you, Juan Carlos.
Next up is Violette Impellizzeri. How are you, Violette?
I'm good, thank you.
Thank you for joining us. So Violet is the program manager of the ALMA node in Leiden. So for those of you who don't know, the ALMA node the ALMA nodes are like the sort of centers that interface between the ALMA observatory and the community of users who use ALMA for their research. So she's based in Leiden, taking care of that particular node. She did her PhD in 2008 at Max Planck Institute for Radio Astronomy in Bonn. And at that time, she was already working on very long baseline interferometry, which is this technique that allowed today the EHT team to deliver this fantastic image of Sagittarius A star. She moved to ALMA in Chile, where she was very heavily involved in the commissioning and testing of the Event Horizon telescope. So if you want to find out how it is observing with these amazing telescopes, Violet is the person to ask. So welcome.
Thank you.
Next up, we have Roman Gold. How are you?
Hi, thanks. It's an awesome day.
Yeah, very exciting for everyone, right?
Yes, yes, very.
So Roman is an assistant professor at the University of Southern Denmark. And he works mostly on the theoretical description of the physics of black holes. And he actually did his PhD in 2011 on the physics of gravitational waves, which are these ripples in space-time that occur when two massive objects, like, for instance, black holes, collide and merge with each other. He was also responsible of one of the papers that the collaborations released today, which is the one in which they take the data and they try to derive the parameters of the black hole at the center of our galaxy. So they try to basically match different properties of the black hole, like the mass, how fast it's spinning, etc., to the properties that they observe with the telescope. So welcome, Roman. Thank you for being here. And last but not least, we have Siri Jonesy. How are you? We cannot hear you. I think you're muted.
Hi, Juan Carlos. I'm doing well. Thank you. How are you?
I'm good. Thank you. Thank you for joining us.
Pleasure.
Sid is a fellow at the UKRI, and he's also working at the Muller Space Science Laboratory at University College London. He's an expert in general relativity. So if you want to find out all the weird things that can happen close to these mysterious objects, black holes, he's the person to ask. All right. So yeah, we're having already quite a lot of questions. But before going that, I wanted to ask all of you, how did you feel watching this press conference? I mean, there were like several of them all over the world, so I don't know who watched which one, but I just wanted to get a feeling of how you felt. Because for people like you who have been working on this for so long, it might be like a really special moment to see this finally going live to the public, right? I don't know who wants to start.
I could start, if that's okay.
Sure.
So one feeling I had is that I was very nervous. Actually, even though I wasn't one on the stage, you feel it because you're right. It's really part of this global team, and there are a few that presented. But even if you're in the audience, you want to have it that it goes well. So you're nervous, but I think in the end worked out really well. And I think then afterwards, very proud, right? Because it's something that we've all worked on for so long, so many years. So then it's a very nice final result that we obtained, and very happy to share it with the public.
How about the others?
Very much the same. Yeah, there's a lot of excitement going on, all kinds of emotions, relief. We're also all a bit tired, I guess, but at the same time, we're looking forward to all of it, and it gives us a tremendous energy to see the response from the public. And yeah, just happy to be here with the entire team presenting this to the world. It feels good.
And on my side, especially since we were in the collaboration, the only human beings who could have access to this image. I mean, we already know the image since a while, and it's very exciting to share this with the world and with everyone. So that's really an exciting moment. Besides you are on the stage or not, it's really a tremendous excitement.
I can imagine.
I really liked why we were trying to watch all of the different press conferences, but Ferial's point about, many of us have worked on this black hole for over 20 years, and you get to meet it, so we met it, as Rocco said, first before, and now we can introduce it. It's really exciting. Yeah, and it was really nerve-wracking, surprisingly.
Yeah, I'll join, I guess, last, but yeah,
extremely nerve-wracking. I think that even though it wasn't a relaxing moment, it was so exciting. And I can't imagine what it must have been like for the people on stage, actually.
I wanted to ask you, did the image feel new or different in any ways? Because you've seen it like so many times that I don't actually know whether you see it like for real, so to speak, whether it feels different. Or you're just so used to it that...
I looked at the face of the people instead of looking at the screen around. We were in a big lecture hall,
yes.
And I was just looking at the others' look, and I could not capture though if it was just shock or yeah, hard to read.
We showed it during in the university in sort of the big open hall, and there were a lot of students there, and everybody started clapping. That's pretty awesome.
Great. If you want, let's start going into the questions, because we have already quite a few of them, so which is actually quite nice. Let me see. So we have a question, for instance, from Twitter, from user Rushi000. This one is, I think it's probably for Sarah. So he's asking, how can the black hole at the center of our galaxy be face on to us, as the image suggests? You know, if you look at the donut, it seems as if the image is facing us. Shouldn't we be able to see the accretion plane rather than the direct center of Sagittarius A star?
Yeah, and that's a really good question, right? Because I think we often have this perception. We think that similar to, you know, how planets are sort of moving in the plane, and Sagittarius star is in the plane of the galaxy, and so you would expect it to be spinning together with it. But actually, the way black holes, their spin builds up is over extremely long cosmological timescales. All of its history contributes to the mass that falls onto it, can spin it up, can spin it down, and change its orientation. It could also have grown by colliding in the past. Other galaxies collided to form our current galaxy. And then those two black holes have their own orientation, and that combines in the net angular momentum. So when we say pointing at us, what we talk about is the axis around which the black hole is spinning. And it turns out that that's actually rather random compared to the larger scale of the galaxy. And right now, for instance, the black hole we think is being fed by a couple of random stars just sitting around it. And that orientation has more to do with the star's orientation than, you know, the greater disk of the galaxy.
So could it be that at some point in the future, again, of course, in cosmological timescales, the axis of rotation could flip and change somehow?
Well, it's at the rate it's accreting now, definitely not. There was somebody said it's like the equivalent of a human eating a grain of rice every million years. I love that. You need to really give it a lot of mass with a very different angular momentum to change it. And I think that that's actually not happening. Maybe in the future if another huge galaxy meets our own, but seems less likely.
Yeah, there's something that reminded me of a question that I wanted to ask, because it's a misconception that sometimes we see among the general public. So there's this idea that black holes are like vacuum cleaners that suck everything around them. And now you're saying that our black hole is somehow in a sort of diet, because it's not eating a lot. So I wanted any of you to sort of explain what actually happens. Like, how close do you actually have to get to a black hole in order to feed it? Are we safe, for instance, at a distance where we are from it?
Yeah, but certainly safe. I would argue it's actually quite difficult to fall into a black hole. You have to get rid of all this rotational energy that you typically have when you're far away from the black hole. And it was a long-standing astrophysical mystery, actually, how so much gas gets so close to the black hole. But once you're too close, yeah, then certainly you're in trouble.
Yeah. Okay, so it's good to know that we are safe where we are. We have a question from Twitter as well, from user Tanya M. Fisania. So she's asking in what wavelength this image was taken, and for how long did you observe in order to take this image? How many hours in total was it required to take this image? So I think it's about Rocco, for instance.
Yes. So we observed this the black hole at 1.3 millimeters, which is the wavelength that allowed us to gather enough resolution for being able to resolve the shadow of the black hole. And we observed this for 5 days, for several hours per day. And then it took long to us to do this because Sagittarius A star is a special black hole. It took us almost 3 years of very, very hard work, as you can see from the faces of everyone here when I say this sentence. And this is mainly for two reasons, because Sagittarius A star is much smaller. It's more than 1,000 times smaller than M87. So that means the gravitational time scales are much shorter. So that means that while we are observing the black hole, it's changing. So it's like taking a picture of something that is moving on. And the other thing is all the plasma, interstellar plasma between us and black hole that is producing the image to be blurred because of all the scattering effects. So for tackling these two issues, we had to develop ad hoc algorithms and techniques. That's why it took so long. And then, of course, there was the COVID in between. So that was a third challenge for that.
I see.
Can I add a comment to that?
Yeah, absolutely.
Yeah, so just to fill in what Rocco is saying, he said 5 days to observe, which is correct. It was observed on 5 days, separate days. Not all antennas observed on all 5 days. And one of the 5 days was particularly good, where all the antennas participated and the best data was achieved. And that's April 7th. And so this image that you see is from that one special day where the weather was good at all the stations all around the globe. Sort of a cosmic positive conspiracy to actually get the best data possible. And so our data for all the 5 days, but one is shown in this particular image.
I see. So actually, since the Earth is rotating, given the configuration of the entire system, is there any point at which all the antennas are facing simultaneously Sagittarius A, or do you always have to sort of combine patches of different areas of the EHT?
You always have to combine different patches of the different, okay. Yeah. You kind of fill out the UV space over time. And the big issue is the variability. Sorry, go ahead, Michael.
Oh, sorry. Yeah, just to add to that, right? We typically start with the Earth rotating, and then we start with Spain that sees it right first, and then continue, and then we have like telescopes in the US and in South of America, and also the South Pole sees it essentially all the time, right? Because it doesn't matter if the Earth is rotating; the South Pole always looks in the same direction. And then finally, we have the telescopes in Hawaii. If the Earth continues rotating, then those telescopes can see it. But then usually at that time, when Hawaii gets online, so essentially right when the source, like the sun, rises at Hawaii, it will set in Spain. So we don't have this long connection.
Right. I guess something that we should probably explain to people is how the data is actually combined, because when we say that that you link the telescopes all over the world, they are not like physically linked, of course. You actually have to ship the data and then combine it in a supercomputer. So could any of you explain, first of all, how do you manage to synchronize the data with the precision that you require to combine the signals? And then why you cannot just transfer the data over the internet, for instance?
Yeah, I don't know. Should I or Violetta? Do you?
Sure. Sorry, there's a background
there's a noise. Yeah,
it's a little distracting right now. Yeah. Okay. Thank you. No, it would be too much data to combine over the internet. It is much easier in a way to actually ship it over FedEx, and it takes longer, of course, and it actually takes particularly much longer in the South Pole, where they have to wait for the window to finish and they can ship it. So it does take a lot of also patience and time for this process to happen. And then there's a post-processing moment where all the data, Michael is also highly involved in that, the data is again reanalyzed and realigned and sort of with special, for the clocks and everything to be exact, to be able to combine the data together. So it's a really slow, painstaking process. But worth it. Yeah.
We have a question here on YouTube from Gerald. So he's asking, have you already been able to derive a short movie sequence of either Sagittarius A or M87?
Yes, I can take this. We made a first attempt, and today actually 10 papers in total, 6 papers in particular were published, and on paper 3, there is this analysis that was being done by a dedicated team just studying the dynamic evolution of Sagittarius A*, but of course this was at this stage more or less a kind of exercise, because we don't have enough good data for being able just to tell with precision how the source is changing. But of course we have more observations taken in the following years, 2018, 2020, 2021, where we had more antennas and we doubled the bandwidth. So hopefully for the future, we will manage to make an actual movie and actually to track the dynamic revolution.
It's probably one of the questions that we were getting most often, because I guess there were some people expecting to see a movie, but as you say, it's more complicated than it sounds. Thanks for answering, Rocco.
Yeah, thanks.
So we have a question from Twitter. This is probably for Siri. So is Sagittarius A definitely a classic black hole, or could be something even more weird, like, for instance, a wormhole?
That's a great question, and it's a question that actually paper 6 directly addresses. So we asked ourselves that very same question, and we looked at alternatives to not just black holes that are described by Einstein's theory of gravity, so that's general relativity, but we also looked at black holes in other theories of gravity. We looked at things like boson stars and objects which actually have surfaces, so they're sort of like almost like stellar objects, but even more compact. We also considered wormholes as well. And we're able, first of all, the net sum of all of this work, and we looked at hundreds of thousands of models of things which aren't Kerr black holes, and we found that the data that we have and that we presented today is actually within 10% of Kerr, which fits within the observational areas that we have. And we can't completely conclusively rule out things like wormholes, although the gravitational lensing structure is very different to what we typically see. So it'd have to be a wormhole which has a compactness or gravitational field that's very similar to the black hole, but we can rule out things like reflecting surfaces that are highly reflective. We can rule out objects which have a bright surface, like stellar objects, like boson stars, with these data, because you see this very dark, pronounced what we call central brightness depression, and that absence of light there. And if we had better resolution, we'd be able to resolve the dynamic range even better, in contrast to the outside, this bright ring. You can rule out objects like that. So we're able to actually exclude things like boson stars on the basis of this kind of data. And we've written papers on this previously too, actually. So check out paper 6.
Okay, thanks a lot. Now, bringing things a bit closer to home, because it's kind of hard to get an idea of how big these black holes, both Sagittarius A and M87 are. So we have a question from YouTube by Said Murtaza. Could you please give us a general idea of how vast in space is the size of this black hole relative to our solar system? I'm gonna share an image here to illustrate it, and maybe Violette, you can answer this.
Great, that is exactly the image I was looking for right now in my computer. I think this illustrates it really, really nicely. So yeah, this is a comparison. Many people felt, okay, this is the size of these two rings in M87 on the left here and Sagittarius A star, similar in the sky, the angular sizes, but they're very different black holes. And so on the left, this is the old picture that was shown 3 years ago, where you have the M87 ring, and then you see, for comparison, the orbit of Pluto and where Voyager is now. So you see how exquisite this was, this angular resolution that was obtained via the AHD observations. But now the new image on the right shows that is even more impressive, because what we're seeing here in comparison to our solar system is, in fact, the orbit of Mercury, which is very close to the sun, and how the sun compares in order to it. So these are really different scales when you think about the size that these black holes occupy in space, right? Not what they look like in the sky, but what size they occupy in their own galaxies.
Okay, thank you. Yep, so pretty clear explanation. Thanks a lot. Since I have the image now here on the screen, I want to take the opportunity to say hi to anyone who is joining us right now. So we are talking with a panel of experts from the Event Horizon Telescope team who has just released the first image of the black hole at the center of our galaxy, which is the one that you can see on the right in your screen right now. If you want to ask questions, you can do so through Twitter using the hashtag AskEHTEU, or using the chat on YouTube here. If you cannot see the chat, just refresh your browser and it should appear visible for you. So let's continue with more questions. We have a question from Twitter from user Zai0Jix. He's asking, will the Sagittarius A image dataset or part of it be accessible to the public?
I think, yeah, I can take that. It will be fully public. Well, actually, it is fully public starting today, and actually at multiple levels. So you have, for once, the data set as was fully processed, where you only need to run the imaging algorithm to get an image reconstruction. So it's a very heavily processed data that also people can use that are not necessarily experts in this field. But we also released all of the raw data actually today, together with all the algorithms that we use to process that data. So it's a lot of software as well that we've written and that we also now properly released. So everyone can actually now take the data, run it through our own algorithms or they can build their own algorithms to actually reproduce everything that we did from scratch, which I think is very important for like scientific reproducibility and also accountability of our results.
Okay, I see. Thank you, Michael. So one thing that probably people are asking themselves, especially those who remember the previous image of M87 from a few years ago, is that last time there was only one image. But now there was something a bit more special. There was like the main image, but then at some point we showed 3 images below that. So I'm going to show the image in the meantime, because we have quite a few questions from people who are trying to understand what exactly does this mean. So this is what we showed in the various press conferences. What you see there is the on top, the main sort of average image, so to speak. But then at the bottom, we have like 4 different flavors of images and with some weird-looking bars next to them. So we are going to try to explain to our audience what this means exactly. So for instance, we have a question from user Pyri Runke. He said, you showed us a composite images of 4 groups of Sagittarius A images. 3 of them had bright spots at different locations, which you can see in the image as a bright blob. But in the image groups, why are the bright spots in different places? So Rocco, for instance, can you explain this? Why do we have these 4 different flavors? And yeah,
sure. I can take this. Yeah, that's a great question. And I mean, this is almost obvious for us who worked on that for 3 years, but it's not really easy to explain. So the main point here is, as I mentioned earlier, that this is a special case with respect to M87. This is because this is a special source. So we are trying to make a still image here of something that during the observations is moving. So this is why we have these different flavors here. So the point is we used several algorithms and we used the millions of combinations of parameters for these algorithms to get all these images. And then the good news was that vast majority of these images was showing this ring with a consistent size. And by clustering, by putting together all these images, we found these 4 actually different families, which all of them have in common the fact that this kind of ring-like, it's the size is consistent, but still we have some uncertainty on the azimuthal distribution, which is exactly where these 3 bright spots are located. Plus, in the last one, you will see there is something that is not really ring-like, but similar. This is just, you know, a tiny fraction of what we obtained there. And to reassure you all, I mean, we obtained the same exactly fraction when we test our algorithms against synthetic models, for which we already know the truth image. And this is just, you know, kind of statistical computation that we expect. So this is the reason why we cannot say where exactly are these bright spots located. And this is the reason why we put these 4 images here.
Okay,
I hope it was clear because it's very complicated. So.
Yeah. Also, I guess we should say to the people listening to us right now that those bars that they see at the bottom, they represent, I guess, the probability in a sort of very loose way that the image could be something like that, or in other words, like what fraction of all your simulated images were found in each one of these.
This is actually the fraction of all the images that we produced. Okay. So, and you see that the vast majority is just the ring-like with the 3 spots, and then a super tiny fraction is the 4 group.
Yeah, so like in the 4th image, that very, very tiny yellow bar indicates that there are very few images that were actually not a ring. So we can say with some certainty that this is actually a ring, correct? Okay, thanks a lot. So we have also a question from Twitter by user ABJ. So he's asking, what is the effect of the flaring activity of Sagittarius A on the modeling of the images at the scale of the event horizon? I guess this is either for Sarah or Roman, but I would like you to first explain to our audience what we mean by flaring. What is this flaring about?
Maybe Roman, it's good if you start talking about the variability, and then I can talk about multi-wavelength flaring. Or
sure. Okay. Yeah. Absolutely. Yeah, so a source like Sagittarius A is observed and known to flare every now and then. There's it's not just a steady shining of light. Sometimes a bit more material gets closely to the black hole, and it produces these more energetic events that occasionally happen from time to time. And they're not only seen by the Event Horizon Telescope, and this is something that Sarah can also particularly well comment on, is also seen and picked up by other observatories. For example, on April 11. Sarah, you probably want to go deeper there.
Oh, okay. Sorry, you're passing to me. Yeah. So, I mean, well, you know, the variability effect, the effect on the modeling, which was sort of part of the question, was something that Roman helped us sort out, actually, right? Was the just general flickering of this thing and then trying to account for that in the noise, you know, this noise modeling. So that was part of what we did. And that was in the, you could read all about that in paper 4. And then there's this aspect that this black hole is basically flaring in, especially also the infrared and the X-ray bands. And so we try to organize these campaigns from space and ground at the same time during our EHT observations, and use these as constraints on the modeling, because these flares seem to be happening right outside the event horizon as well. Now, we can't make images of these flares in the infrared and the X-ray, but we can combine this with our EHT images to see. And we didn't really explore that fully in this first round of papers. We mentioned it, as Roman said, on April 11th was the cool day where we managed to, unbelievably against all odds, catch a flare in the X-rays during our campaign. And we see that the variability of Sagittarius A does seem to change. But we don't know what that means yet. And that's going to be a very important thing for us to try to figure out in the coming period.
Just to fill in what Sarah commented on. So there's also a difference between what we call a flare and a more general typical variability that occurs in the source all the time. For example, the technique that was developed and presented in paper 4 was more looking at Sagittarius A*, how it always tends to vary over time. You know, there's this constant bubbling going on in the source, and it produces a very distinct fluctuation in our data. And we needed to develop a new technique to incorporate that and inflate the error bars accordingly in a very careful manner to allow our previous imaging methods and modeling methods to be applicable. And then if a flare like on April 11, for example, happens, that's a different kind of variability, and it requires a different take from the modeling side.
Speaking of variability and material passing by the black hole or even falling into it, we have a question on Twitter by user Alex Cadet. He's asking, is it possible to observe jets at such a distance? Any estimates of, well, this is also a different question. Any estimates of the mass of our galaxy with the new data? But I imagine that they probably refer to the mass of the black hole itself. But let's go with the first question yet. Would it be possible to observe jets at this distance? And in the specific case of this particular black hole?
I would love to take that one because I've been trying to find jets in Sagittarius A for a long time. Well, so the point is, actually, even if Sagittarius A* were launching very small jets, and we think there's a pretty good chance, I mean, at least the models that we use predict there should be jets, but we have to remember that Sagittarius A is basically something like tens of or 100,000 times less powerful than M87. So if you just turn the crank down, its ability to make powerful jets is hampered. And then you have this complicated mess in the galactic center, and trying to pick out some weak feature, we already have known for a while that it would be quite difficult to see. So the question is whether, when we have our upcoming data sets from the coming years, when we have more telescopes, and we also fill in some of the baselines, will we be able to maybe connect this, fuzzy sort of donut thing to maybe some kind of extended emission? It's the same issue we'd like to do with M87. The question about the mass is, I mean, about the galaxy, we're on such tiny scales that we wouldn't be able to get a new constraint. But I would say, in terms of constraining the mass, we do constrain the mass in our publication. It's just that we don't do as good a job as has already been done by the Nobel Prize winners of Andrea Ghez and Reinhard Genzel's groups.
I guess you could say that in a way, like the orbits of the stars are the black hole provide you like a more direct, a more straightforward way of getting the mass rather than the kind of modeling you have to do with this data, right?
Yeah, I mean, Kepler's laws are pretty easy, in some sense,
exactly.
They have extremely, precise data. So.
Even though we mentioned briefly the mass of the galaxy, which, as you say, you cannot constrain because the scales are very different, I wanted to take this opportunity to also tackle another popular myth that goes around sometimes, which is the idea that because supermassive black holes are at the centers of galaxies, that they are somehow responsible for the galaxies spinning around them. So I wanted, any of you to briefly explain why this is actually not the case. Like, what would happen if you remove the supermassive black hole in the Milky Way, for instance? Would the rest of the galaxy notice? I don't know. Whoever wants to take this question. Otherwise, I will assign any of you. So, Violeta.
The short answer is, if you were to remove it now, probably nothing. That's what would happen. The question is what role it had in the formation of our galaxy, and that in the fact that it looks like it does now. But the sphere of influence of the black hole itself on its surrounding is not very large. It's very small. So if you remove that, it wouldn't impact us directly. But maybe the evolution would change again. So I don't know if somebody wants to elaborate on this, or has different. Is more worried than I am.
Maybe a more indirect effect. I mean, the jets have been mentioned before, right? Sarah liked them very much in Sagittarius A. Unfortunately, we haven't seen that yet, but we see it in other galaxies, right? In M87, there's a very, very clear indication of a jet. Another galaxy, for example, is Centaurus A, where we also imaged a jet. And when these jets, when they plow through the galaxy, they actually impact the gas that is in the galaxy itself. It may be compressed, it may be heated, and that might trigger or actually hamper. It's a relatively active field of research, trigger or hamper star formation. So you may actually have the influence from the jet or other outflows from the central black hole. It's not only accreting, it's also putting stuff out there, and that might influence the whole evolution of the galaxy.
Okay. So we have a question from. Sorry, go ahead.
Yuri wanted to.
Sorry, I didn't see you. Sorry.
No, it's okay. I just wanted to quickly add to that about the jet stuff because I think it's really interesting. That we see evidence of a very violent past for Sagittarius A star for our galaxy. We have these things called Fermi bubbles, which are these enormous radio lobe-like structures which extend above and below the plane of our galaxy. So they speak to some very violent, almost cataclysmic event that happened a very long time ago. And it's curious that we're in a period right now where everything's very quiet. And probably in some way a jet of some description or some enormous eruptive event is responsible for that. And so I think, what's really cool about these observations is we don't see a large-scale jet, as Sarah and Michael have said, but the question really is, why don't we see one? And yet, in the past, we seem to have indications there may have been something like that. I think it's really cool that we're having this rare opportunity now to finally have a look at the very heart and maybe start to answer these questions in time.
Yeah, actually, sorry, just a thought that occurred in my mind, and I wondered what would happen if Sagittarius A had a jet like M87, right? What would that mean for us? Maybe not good things.
Luckily, it's pretty far away, so.
Yeah, we should be safe from it, right?
And it's not in the center of our galaxy.
Exactly. I have a question for Violeta. So from Daniel Tapia. Someone mentioned in the American live stream that there are plans to observe this whole Sagittarius A at different wavelengths to be able to detect more features. So he wants to know, first of all, what wavelengths these are, and also would you be able to resolve the black hole shadow with these as well?
Yeah, so yes, the EHT has been very active since these observations, and it will be further active. It's more planned ahead. Some observations have been taken. So these are 2017 observations, and observations have carried out the following years just to look back before looking into the future. We have observed in 2018, so the year after. There was a gap between 2019 and 20, also due to the pandemic and other constraints. And then 21 last year, and this year, 2020, a month ago, there were more observations. But there's more to come. So more observatories have joined. So it's not just more new wavelengths, more observatories have joined. and notably offering new baselines and covering the UV plane. That virtual telescope of the size of the Earth is getting, filled up more nicely, and you can find more structure, also more larger scale structure, as Sarah was pointing out before. But yeah, going back to the future, so what is planned for 2023 is really exciting for DHD, and also exciting for those of us who worked towards it in the past, is the addition of a new frequency, a new band, which is higher frequency. We call it band 7 in jargon, so it's even higher frequency than what we're showing in this image. And it will allow to see potentially even closer to the black hole, because at high frequency, the resolution is improved as well.
Right.
So it is extremely exciting. And so that's to come in 2023, that's next year.
So let's stay on this topic, because we have a question from Sam on YouTube. So he's 14 years old, but very interested in astronomy. So he wants to know what is the next stage with the EHT. So I don't know if maybe Rocco or Roman want to elaborate a bit more on this.
Sure, I can take it. So I like to stress that this image we present today, which is in the background of Sarah, actually this is an image of a single day of a single year, 2017. So we have more days on the same year, and then we have additional observations in the following years, 2018, 2020, 2021, 2022, as Violetta also mentioned, which means we will be able to track the structural changes and time evolution of the source. And except from, it's not only Sagittarius A and M87, we also have other targets, as Michael mentioned earlier, like Centaurus A, and then we have another binary black hole system candidate, which is OJ27. And besides this, we have more targets, and we also polarized light emission that we observed, so we can study the magnetic fields. So we have so many science cases to address in the next year. So the best maybe is yet to come. I don't know. I hope so. So Roman, if you want to add anything else here.
Yeah, absolutely. Yeah, there's a lot of science cases, and they tend to grow, the number of science cases with the better the observatory gets. Adding stations in particular is such a useful thing. It enhances our sensitivity in the image. We allow ourselves to be more sensitive to the low brightness features, for example, and taking more data reduces effectively the time over which we can generate an image. It's like exposure time, basically, if you think about photography. And so, yeah, that will hold tremendous promise in moving forward, and allows us to ask different types of questions in the future.
Can I also add something to that?
Yeah, absolutely, yes.
Because really, like for the very far future, really the holy grail for us has all been to go to even longer baselines, right? Right now, kind of limited by the size of the Earth. We have our telescopes around the globe, and that size of the Earth determines our resolving power, right? That we can see these black holes. But there are also plans, as I said, far future ideas to launch satellites, like to launch really satellites with telescopes on them in an orbit around the Earth, like something like Chandra Observatory or the Hubble Space Telescopes. And we could then use these telescopes as an extension to our network, and with that we would get an even higher resolution, and we'll be able to take more pictures of even more black holes. So that could really blow up this whole field of research. So for someone, I think the question was asked by someone who's 14 years old. So for someone who is like an aspiring astronomer and who is now 14 years old, right, for their career, that might be like a real possibility.
That's fantastic. Actually, I wanted to ask, I don't know, any of you, if someone wants to, if we have like more of these young future astronomers, what is the path that you think they should take if they want to pursue this as a career? It's a tricky question because, of course, there's not a single path. But I don't know if any of you wants to explain very briefly how they should go about doing this if they want to do this for a living. This is for anyone. I don't know.
Maybe I could say something because I didn't take a very typical path, so it's maybe
perfect.
In the US, we don't have to focus our studies until we get to university, and I actually was doing more arts. I was thinking I was going to go to art school, and I was just interested in science and physics from reading a lot of science fiction and comics and all that kind of stuff. And basically, I just started studying it in university and really liking physics. And then it was just curiosity driven from that point forward. So honestly, I never set out to do this, and I never thought I would succeed in doing it. And I think that if I can do it, anyone can do it. So I think it's a really great thing to just be curiosity driven and try to just study what you find interesting.
Yeah, that's great.
Yeah. Can I add just a thing? I really like Sarah said science fiction, because I was going to suggest to read science fiction as one of the paths. I think that really gets your mind sort of broadens a little bit what you think is possible and what is not. And also, once you get to a bit older, maybe university stage, don't be shy of approaching people who you think do cool work, and create those connections early on, because maybe there is stuff for you to do there already, you know, as a student. Yeah.
Yeah, I think like if you talk to any random astronomer, like the chances of them having followed a completely different path are really high. So I guess that's also like a really good advice. Like, don't try to obsess perhaps with following a predefined path, because you never know where you're going to end. I have a couple of questions for Siri. So we have several people, for instance, on YouTube, we have the RSC Planetarium in Calicut, asking about, now that we have the first image of Sagittarius A star, how much does this image conform with the expectations of the different models and simulations? And we also have someone else asking, are we learning something new about gravity or general relativity with this new image?
Right, so that's quite a lot to unpack there. I'll do my best to be brief. So in terms of the models and the simulations, so in the end we ended up calculating, I think, around 1.8 million images at a few different wavelengths of what the state of the matter around Sagittarius A star would look like at any given time. And we had a lot of constraints to play with this time. So we didn't just have the 1.3 millimeter or 230 gigahertz constraints. We had constraints at a few other wavelengths, including the infrared. We had variability constraints at very high energies. We have constraints also on the source size and asymmetry and so on. So we had a lot more constraints to play with. And when we applied all of those constraints to the many models that we created, it turned out that many of them didn't make the cut, and only a few survived. And those models which survived, they have a few common properties. And one of the first is that they tend to be in what we call a magnetically arrested state. So they're extremely magnetized. So they have a very high magnetic flux and have a very thin current sheet near the event horizon. They're just very dominated by magnetic field. We also found that the models that we're creating favor an inclination angle which is closer to face on, which was surprising. And we also found that most of our models favored a distribution of radiating electrons, which basically necessitated the presence of a jet, which is something we don't actually see, but like a base of one. So a lot of those electrons were pushed outside of the plane and further away. And that's quite interesting too. And so it's actually quite a surprise that a lot of models were ruled out. Now, in terms of the other question, which is about general relativity and what do we learn? Well, we learn that, if I may say in British slang, Einstein did a bloody good job. And it turns out that his theory is remarkably consistent. I want to emphasize that this is the second time he did a black hole. And of course, this is special because this is our own supermassive black hole. But there's a difference in mass here of over 1,500, factor of 1,500, and yet you see morphologically the structure of this ring is basically, it's consistent across these extremely different mass scales, which speaks to the macroscopic properties of black holes and the fact that this is a regime where gravity dominates. And just to give you a sense of how well, my final comment on how this speaks to validity and robustness of general relativity. So I've got a number that I like to quote, which is, so we find the ring diameter in these measurements. If you convert it to kilometers, it's about 63 million plus or minus 2.8. Now, if the black hole isn't spinning at all, so it's as large as it can possibly be, you get a number which is of the order of about 64. So it's right in the smack bang in the middle of what we find. And we don't take this image and just put a ring on it. We actually work with the interferometric data and we find a ring in that data. It's a Fourier transform of one. So we don't literally fit, there we go. We don't fit a ring to that. We actually look at the visibility data. But the point is we find something remarkably consistent with general relativity. I think that's just amazing.
Yeah. Yeah, it's incredible that that the theory gets so many things right down to that level of accuracy, right?
Yeah, indeed.
All right, so we're having quite a lot of trouble scanning through the questions because we have like so many of them. So we really, really appreciate the interest that you are showing. I have a question for Sarah by user Spider Shan. They are asking which targets are being considered by the EHT for future observations.
Well, I think this sort of touches a bit on what Michael was talking about. Sorry. There's Michael Johnson and Michel Janssen in our collaboration. We're always doing this. But at the moment, right, we're limited by the size of our planet. So in terms of the ones that we can actually see the ring, it's just these two, M87 and Sagittarius A. But we actually have quite a lot of other black holes where we can see the inner parts of these jets. And for all these reasons we've been talking about, the fact that these jets can actually alter, the entire evolution of their galaxy, as well as accelerate the highest energy particles. We're really interested in these. So we have targets we've already published. 3C279, Sen-A, there's many more in the pipeline. And then the thing that's going to be very interesting is when we start to move into this, space, because I think there we open ourselves up to an entire population. And, so that's going to be, the long-term future. And the intermediate future will be what we call sort of the NGEHT expansion, when we start to put baselines on the Earth that won't get us more horizon targets, but will get us many more of these supermassive black holes and jets. And I think that's going to be very interesting because, when we try to assess this whole population of these black holes throughout the universe, they're in all different shapes and sizes and all different types of powers. And we need to have a full population to be able to fully understand them, their evolution, their relationship to their galaxies. We need to understand this in multi-wavelength. And so you can imagine there'll be many, many years of observations as the telescope expands outwards in size and scope, together with multi-wavelengths.
I see. We talked before about whether we are safe or not from the black hole. We have a pretty interesting question here. I guess this could be for anyone. It's by user, I hope I pronounce this correctly, Chassis Earth Project. They're asking that since we are positioned face on to where the jets are supposed to be, what would happen if they should turn on or start firing up? Would we be in danger if we are looking directly at any possible jet that could come out? Any of you? I don't know.
We sort of talked about it before, right? I mean, Ziri was mentioning that there was a lot of activity in the past. I think we're pretty far away. So even if the jets did become more active, we're sitting right next to a pretty dangerous source as well, which is the sun, and it's bombarding us constantly with the same kinds of particles that the black hole is basically emitting. And so as long as it stays far away, our Earth's magnetic field, thankfully, is keeping us pretty safe from these types of particles. But you can imagine that if we were on a planet much closer to the jets, in fact, they could be quite catastrophic for life. Yes, so it's an interesting question, and maybe some unlucky aliens out there have to worry about this.
Okay, let's see. Yeah, sorry, apologies, 1 second. There we go. So this is a question, I guess, for everyone, but maybe Sarah, I guess. We have a user, Cider NEHC, on Twitter asking that since we observed the Sagittarius A star and we took pictures of it, what other features are still unknown? Other than the rotation direction of the black hole or the jets that can be seen right now, what is other stuff that could be crucial about the black hole, but we don't know yet? Anything that you could potentially discover that you haven't found yet?
I'm sure all of us have answers to this. I have one I could just start with, and that comes down to this flaring, actually, and the relationship to the activity and the feedback that this black hole can, impose and damage and sort of shake up its environment. There seems to maybe be a connection between this because Sagittarius A is the absolutely weakest in terms of how much material it's eating and how bright it is. It's the weakest black hole that we can currently observe, so it's very, very dormant. And yet it seems to have these very interesting flickering flares that we don't see in other black holes. And other black holes, pretty much all supermassive black holes and stellar mass black holes that are, sort of eating but not eating a lot, So we call them sort of weakly accreting black holes, but they have jets fit on a very tight plane. They basically have a very tight relationship between the energy coming in, the energy going out, and their black hole masses. Sagittarius star is the only one that we know of that doesn't fit on this. And it's very interesting to think that maybe it has to do with the fact that these jets aren't there, or the jets aren't being somehow lit up by particles. So for me, that's a really pie in the sky kind of interesting question that hopefully we'll be able to learn more about in the coming years.
Does anyone else want to add anything?
Yeah, I guess one more thing about the detectable features in the future. It's really striking that there's a whole hierarchy of things that we can observe here. And it starts with what we call astrophysics sometimes, what the gas is doing around. That's usually the thing we're very sensitive to. But then we're trying to dig into other features about gravity, and that has to do with the ring and its persistence. And hopefully it doesn't depend on the wavelengths that we already discussed in the previous questions, and so on. And all these questions we can answer better and better just by keeping monitoring and looking at these sources for a longer time.
That's it. Well, unfortunately, we are running out of time because we should finish at 5:30. But I don't want to leave without getting your last impressions of this image. So I would like to go to do like a round and ask you to describe this image with like one word. Like if you had to use one single word to describe this image, what would it be? So let's start with I don't know, Roman.
I would say it's a ring. It's a little bit more than one word, I'm sorry. But
that's okay. One ring to rule them all, I guess. How about you, Violetta?
This is a really tough exercise because I can only think of sentences like Robert. I think I would say it's inspiring, also humanly inspiring because of the work of all the people behind.
I see. How about you, Rocco?
So I would say the universe is full of donuts. So
that's always good news, I guess, right?
Yeah, Homer will be happy.
How about you, Michal?
Well, yeah, I mean, Violetta already said inspiring, so I was trying to think of something else. I would say maybe rewarding for all of the work that has gone in trying to produce this amazing result.
How about you, Siri?
Tough question. I'd probably say magnificent. Magnificent that we're finally, as a civilization, able to see the heart of our own galaxy.
I completely agree, yeah. And finally, Sarah, how about you?
Oh, me? I'm sorry.
Yeah.
I mean, everyone said it. You know, I still think we live in such an amazing time that you know, billions of people have lived before us, and yet we're the ones that are currently on this planet that can see this. And I think, you know, other people point this out, but other aliens elsewhere in the galaxy will look and see the same thing. So it's something really universal. It's the galaxy. It's our black hole, and it's just familiar and amazing.
Mm-hmm.
Well, unfortunately, we are running out of time, so I want to thank all of you again for having joined us this afternoon to explain to the audience everything behind this magnificent, unique, historic, however you want to call it, image that we saw today. I'm sure that everyone online appreciate you giving some of your time to share your expertise and your contributions to this story. So once again, Sarah Markov, Michal Jansen, Roman Gold, Violetta Impellicelli, Rocco Lico, and Ziri Junsi, thank you so much for being with us.
Thanks to you.
Thanks for having us.
Thank you.
Thank you.
Bye-bye. Thank you.
And to everyone else who has been following us, we hope that you have enjoyed the press conference and this live Q&A event. You will be able to listen to everything in a recording in case you missed some part of the event. Don't worry, everything has been recorded and you will be able to listen to it afterwards. And thanks again. We hope that you have enjoyed this beautiful image.
Imaging a black hole seems like an impossible dream. After all, they are black and do not emit light. So how can we see them? Well, with a telescope big enough, we could at least see the immediate surroundings of the largest black holes. The supermassive ones that are millions or even billions of times heavier than our Sun. Then we would be able to unveil some of the mysterious secrets these monsters hide. Except that when you do the maths, you find that to observe even the closest supermassive black holes, you'd need a telescope the size of the Earth. Something beyond our wildest dreams. Or maybe not. A few 300 astronomers from nearly 80 institutes across the globe joined forces and found a way to create a telescope as large as our planet. And they did it without using new mirrors, screws, or steel. Their Event Horizon Telescope, or EHT, is not a real telescope, but a virtual one. The stroke of genius of the EHT collaboration was in using powerful radio telescopes that already exist, including ALMA and APEX, co-owned by ESO. They combined their observations in a way no one had ever attempted before, with a technique called very long baseline interferometry. This may sound like sci-fi, but it actually works, as the EHT team showed back in 2019. That's when they revealed the supermassive object at the center of the M87 galaxy to the world. The very first image of a black hole. To understand exactly how hard that was, let us drop in some facts. First of all, you should know that the EHT telescopes could not see the black hole itself, as it is invisible. Rather, they picked up the radio signals from the hot glowing gas around it and imaged the shadow the black hole casts on it. To do this, the telescope antennas in the EHT array had to be pointed exactly the same position in the sky at exactly the same time. The EHT can tell if one of these antennas is off by just a millimeter, and if the timing is by a trillionth of a second, even though the telescopes are located thousands of kilometers apart. Imaging the black hole in M87 then required combining the observations of all telescopes in the network using interferometry. This technique works best if you have many telescopes, which wasn't the case. The team had 8 observatories, though now the network has grown to 11. So the EHT researchers had to develop special algorithms to be able to fill gaps and reconstruct their image. It was like staring at a puzzle with most pieces missing, trying to figure out what the whole image would look like. To determine if the result was scientifically bulletproof, they used a variety of methods. Computer simulations to identify errors introduced by their telescope network, different teams working in isolation on reconstructing the image in different ways, new techniques and software. It took years of work until they were sure they had done it right. Only then did they show their image to the world. The result was like peering at the black hole in M87 with a telescope almost the size of the Earth, an instrument so powerful that it could see details as small as a donut on the moon. So what's next for the EHT? The team have already pointed their telescopes to a new target, Sagittarius A star, the supermassive black hole at the heart of the Milky Way, our black hole. Sagittarius A star is much closer to Earth than the supermassive black hole in M87. So you may think that imaging it is a piece of cake by comparison. Sorry to disappoint you. It's even more difficult. First, The center of the Milky Way is obscured to us by clouds of dust and hot gas that scatter the radio signals coming from around the black hole. Furthermore, because Sagittarius A star is about 1,500 times less massive than its cousin in M87, its radio signals change far more rapidly in time. Blobs of plasma orbit it in just a few minutes, whereas those in M87 orbit the black hole every few days. This forces astronomers to adapt their algorithms and to develop new techniques to get stable images. A bit like trying to read the brand on a basketball while spinning it on your finger. In the end, the EHT team did manage to overcome all these obstacles. So here it is, the first image of Sagittarius A star, the black hole at the center of the Milky Way.